Hello and welcome to this lesson, which is part of the Forces of Motion module for OCR A-Level Physics in the topic of Newton's laws and momentum, looking at the concept of momentum and impulse. So if we've been successful and we've learned in today's lesson, we should be able to define and describe momentum and impulse, calculate momentum and impulse, and link momentum and impulse to Newton's laws of motion. So in this lesson we're going to look at the following part of the OCR A-Level Physics specification. In particular, looking at linear momentum, that net force is the rate of change of momentum, the impulse of a force, and how it links to force-time graphs. So, linear momentum is how difficult it is for an object to change its motion when it is moving in a straight line. If it is difficult for an object to change its motion, it has a high momentum. If it is easy for an object to change its motion, it has a low momentum. Now, the concepts of momentum and inertia are very closely linked to each other. Inertia describes an object's resistance to change in motion or lack of motion, and momentum describes how much motion it has. So momentum is your force or speed of movement, but inertia is what keeps you going. So momentum represents the amount of motion an object has. So we can think of it as a measure of the kinetic energy of an object. Now, inertia is a characteristic of an object that resists changes to its state of motion. Now, objects which are harder to move or whose motion is harder to change will have more inertia. So, momentum is a vector quantity because there's a product of a vector quantity, velocity, and a scalar quantity, mass. So momentum has both magnitude and direction, and its direction is the same as the direction of an object's velocity. So, linear momentum of an object is dependent on two factors of the object, the mass of the object and the velocity of the object. Now, we can express this in the form of an equation, that momentum is equal to mass times by velocity. Now, this is why momentum is similar to kinetic energy. It contains the same terms. So whilst momentum is mass times by velocity, kinetic energy is a half times by mass times by velocity squared. Now, we can symbolize the equation for momentum as P equals mv. Now, linear momentum is given the symbol P as it is the first letter of the Latin translation of momentum or impetus. Now, Isaac Newton realised that a resultant force was needed to change the velocity of an object. Now, Newton realised that the effect of the resultant force depended on the object's mass. Now, it's better here to term mass as inertial mass. So what he decided to do was simplify this system and consider the products of inertial mass and velocity, which he called the linear momentum. Now, what this means is that for objects with the same linear momentum, the larger the mass, the lower the velocity, and it means the smaller the mass, the higher the velocity. Now, the units of linear momentum are kilogram meters per second. Now, if an object is not moving, then it has no momentum. So we say momentum is a dynamic quantity. So every object which is in motion will have a non-zero momentum. Now, an object which is stationary will have no momentum, because if velocity was zero, well, then momentum would equal zero. So, linear momentum is a vector quantity. The direction of a momentum is shown by the sign of the calculated value, either a positive or a negative. Now, objects moving in opposite directions have opposite signs. So this means that momentum can be changed by either altering the speed or the direction of the object. Now, unless stated in the question, you can assign which direction is the positive or negative in a question. So as we know, momentum is equal to mass times by velocity. Momentum has both a magnitude and a direction. It is a vector quantity. If objects are moving in opposite directions, they have opposite momentums, and this is signified by one value being positive and the other being a negative. So this indicates to us that the momentum is directly proportional to the mass of the object as long as the velocity of the object is constant. And it also indicates to us that momentum is directly proportional to the velocity of the object if the mass of the object is constant. Now, this allows us to write the laws of motion in terms of momentum. So Newton's first law, which is that objects either stay at rest or move with constant velocity unless acted upon by a resultant force, could also be said as a resultant force changes the linear momentum of an object. Whilst Newton's second law says that the resultant force equals the inertial mass times by the acceleration, we can write this as a resultant force is proportional to the change in linear momentum every second. And finally, we say Newton's third law is when two objects interact, they exert equal yet opposite forces of the same type on each other. Or we could say that for a system of objects, the total linear momentum of the system before equals the total linear momentum of the system afterwards, as long as there are no external forces on the system. Now we can calculate the linear momentum of any object when considering its motion. So for example, George Russell is driving in the French Grand Prix. The total mass of Russell in the car is 710 kilograms. He is travelling at a velocity of 120 meters per second. What is his momentum? Well, momentum is mass times by velocity, so it is 710 times by 120, so it's 85,200 kilogram meters per second. Now we can consider Newton's second law of motion for a constant mass. We know that F equals ma, and we also know that a is equal to the change in velocity over the change in time. So we can substitute that into that equation and say that F is equal to m delta v over delta t. Now we know that a change in momentum, delta p, is also equal to delta mv. So therefore, if we say that F equals delta mv over delta t, it says to us that the resultant force is equal to the rate of change of momentum. Now in this example, the resultant force must be in the same direction as the change in momentum. So this equation can predict the motion of an object subjected to forces, even when the mass changes with time, for example with a rocket. So this makes it an equation which can be used in more situations, not just a special case. So this statement effectively defines what we mean by resultant force. It's an interaction that causes an object's momentum to change. So we know that if an object's momentum is changing, there must be a resultant force acting upon it. Now we can find the size and the direction of the resultant force by measuring the rate of change of the object's momentum. Now remember, the change of momentum is the final momentum minus the initial momentum, or mv minus mu. So we could write the equation to be F equals mv minus mu over t, or F equals mv minus u over t, which therefore simplifies out again to F equals ma. So this shows us that the equation F equals ma is a special case of F equals delta mv over delta t for when acceleration is constant. We can finally write this out to say that F delta t is equal to delta mv. Now this is important because we can then define F delta t and delta mv as the impulse. So the impulse is a force that is applied for a certain time. The impulse causes a change in the linear momentum of an object. Now impulse is measured like momentum in kilogram meters per second, or more commonly Newton seconds. It refers to one object in a collision, and we know that the larger the impulse on an object, the greater its change in linear momentum. So we can define the impulse to be the product of the average force and the time taken for which the force acts on the object. So for example, we can calculate the impulse of any object when considering its motion. So calculate the impulse acting on a 900 kilogram car when its velocity changes from 5 meters per second to 30 meters per second. Now we know momentum is mass times by velocity. The initial momentum is 900 times by 5, which is 4,500 kilogram meters per second. The final momentum is 900 times by 30, or 27,000 kilogram meters per second. So the impulse is the change between the two values, which is 22,500 kilogram meters per second. We can also calculate the force acting on any object when considering its motion. So a train of mass 7,500 kilograms is moving with a momentum of 150,000 kilogram meters per second. The train driver applies the brakes for 15 seconds and the train's momentum decreases to 37,500 kilogram meters per second. Calculate the force applied by the brakes. So we know F is equal to delta mv over delta t. So delta mv is mv minus mu over delta t, so it's 37,500 minus 150,000 divided by the time, which is 15 seconds. So it's minus 7,500 newtons. The negative is important because it indicates to us that the force is acting in the opposite direction to motion. Now, this concept can be used for any collision between objects such as them rebounding off walls. So if you've got an object which is rebounding off a wall, we can say that the initial momentum is equal to mu and the final momentum is minus mv. Now, in this instance, the velocity is a negative as it's now acting in the opposite direction and momentum is a vector. So we know that force is equal to the change in momentum over the contact time. So the change in momentum is minus mv minus mu over t. Now, if we know that the collision was elastic, well, we can say that mv will equal mu in terms of magnitude because no energy is dissipated out of the system. So therefore, we can say that the change is minus 2 mu over delta t. Now, if the impact is oblique, then the horizontal components must be considered for this. So therefore we know that v would now become v cos theta and u would equal u cos theta. So if we had it now at an angle, it would be minus m cos theta v minus m cos theta u over t. And that allows us to work out the force acting on an object where the momentum is changed by rebounding. Now, this also indicates to us that the lower the rate of change of momentum for a collision, the lower the resultant force produced on the objects colliding. So when the impact time is large, the resultant force produced on an object colliding is small. So if a speeding car crashes, then the time of the collision is very small, so the force can be huge, so this can be very dangerous. It's important to remember that the rate of change of momentum for an object is directly proportional to the impact force exerted on it, which, as we said before, is another way to express Newton's second law of motion, F equals ma. Now, in fact, vehicles are designed to minimize the force exerted during a collision. That is why cars have crumple zones at the front and back. They're weak enough to crumple, but strong enough to do so slowly. This increases the time to change momentum, the rate of change is lowered, so it decreases the resultant force on the car. Car passengers have similar protection. Airbags and seatbelts help increase the time it takes for the passengers to stop. As the time to change momentum increases, the resultant force on that object, the person, decreases. So seatbelts will stretch slightly, increasing the time taken for the wearer to stop, lowering the rate of change of momentum. Airbags inflate before you hit the dashboard of a car, so the compressing air inside it slows you down more gradually than if you just hit the hard dashboard, lowering the rate of change of momentum. Bike helmets contain a crushable layer of foam which helps lengthen the time taken for you to stop in a crash, lowering the rate of change of momentum. This reduces the impact on your brain. Now, crash mats and cushion playground flooring increases the time taken for you to stop if you fall on them, lowering the rate of change of momentum because they're made from soft compressionable materials. So the crash pads and the cushion playground flooring will increase the time taken for you to stop if you fall on them, lowering the rate of change of momentum. So imagine trying to catch an egg. If we held our hand out and didn't move it, the egg would smash because the change in momentum, the impulse, happens in a short time, increasing the rate of change of momentum, making that impact force large. If we cup the egg and move our hands down as we catch it, we make it longer to come to a complete stop. This increases the contact time, lowering the rate of change of momentum, decreasing the impact force, and the eggs remain intact. If we imagine catching a cricket ball, if we didn't move our hands, it would hurt when the ball stopped in our hands because the change of momentum, the impulse, happens in a very short time, increasing the rate of change of momentum. This means the impact force is large, so you can break your fingers. So if we make the contact time longer, we reduce the impact force in our hands from the ball as it decreases the rate of change of momentum. And this is why cricketers move their hands down when they catch the ball. Now, packaging, especially for fragile items, uses bubble wrap or polyester packaging to reduce the impact forces that items experience in transit. This helps cushion the items by increasing the time over which they experience a force, lowering the change of momentum rate, which reduces the risk of damage. And in football, increasing the contact time is sometimes used to an advantage, as the longer the contact time, the larger the change in momentum. So when kicking a football, after a strong kick, the motions follow through. The momentum from the foot is then transferred to the ball. This creates a larger impulse, and then the ball has a higher velocity. So as we know, force is equal to the change in momentum over time, or the impulse over time. This is the force that's produced in the collision which changes the momentum of the object, which we call the impact force. So as we said before, whilst the total momentum of the system of the object stays constant, the momentum of one object can change. Now in many collisions, the change in momentum is the same regardless of the time of the collision. The aim of all collisions involving humans is to have a low impact force. It decreases the chance of injury, and this is done by increasing the contact time as it decreases the rate of change of momentum. Increasing the contact time decreases the impact force experienced by the object. So as we mentioned before, crumple zones, padding, helmets, sidebars, crash mats, seat belts all increase the impact time for a collision, so the impact force experienced by an object is reduced. Remember, it's important to note that the change of momentum stays the same. So when the time taken increases, the rate of change of momentum decreases. So when the time taken increases, the change of momentum every second decreases. Now we can also show this information in a force time graph. In real life, forces are often not constant and will vary over time. So if the force is plotted against time, the impulse is equal to the area under the force time graph. Now since the area under a curve is the y-axis times by the x-axis, it's force times by time, which as we know is the change in momentum or the impulse experienced by the object. So as we can see in a force time graph, the area under the line is going to be the change of momentum or the impulse. Now this is extremely useful when the force exerted is not a constant value for the collision. In this situation, to find the change in momentum or impulse, you must either count the squares or break up the area into different shapes. So you can see here the force time graph for a constant force and also for a changing force. But please do remember that as the impulse is the product of the average force exerted and the time, the area under a force time graph is always equal to the change in momentum even if the force is changing. So that brings us to the end of today's lesson, where we've looked at linear momentum, the vector nature of momentum, how net force is the rate of change of momentum, the impulse of a force, and the idea impulse is equal to the area under a force time graph. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe momentum and impulse, calculate momentum and impulse, and link momentum and impulse to Newton's laws of motion. So thank you for watching this lesson on momentum and impulse, which is part of the subtopic of Newton's laws and momentum in the module 3 forces of motion, which is part of our OCR A-Level Physics specification. Thank you so much and have a lovely day.